Assalamualaikum and greetings everyone. Today's topic is on surface integral. So this is a new chapter. In this chapter we have four sections. The first section is on surface integral of a scalar field. The second is surface integral of a vector field. The third is on Gauss theorem, and the fourth section is on Stokes theorem. Okay, let's proceed to the first section, which is surface integral of a scalar field. Okay, suppose we are given a surface sigma. Okay, so here we have a surface sigma shown in the diagram, and a function. So here we have a scalar field. Fx, y, z is a scalar field, or another name for that is a function, where the function is defined and continuous on the surface sigma. Then the surface integral of a scalar field fx, y, z over surface sigma is denoted by this notation here. So we have fx, y, z, which is a scalar field. We want to integrate over surface sigma. Okay, so to evaluate the surface integral, what we need to do is we're going to project our surface sigma here onto a region which is going to be on a plane. Okay, so we're going to transform it into a double integral over a region. Okay, all right, now let's concentrate on the diagram again. So here we have the surface sigma. So when you take a piece of that, let's say this is going to be equal to delta S. So we're going to just take a piece of the surface, so let's call that delta S. And the projection of that piece of surface onto the xy plane, which is a region R on the xy plane, and let's call that piece of region as delta A. And here, N, so that should be a capital N, sorry about that. This is a normal vector, not unit normal vector. So n here is a normal vector to the surface delta S, and k here is really the normal vector to the delta A. So a normal vector to delta A would be pointing upwards, and so it's equal to k, which is equal to 0i plus 0j plus 1k. All right, so that is the normal vector to the surface delta A, and n here is the normal vector to the surface delta S, and gamma here is the angle between the two normal vectors. Okay, now let's look at the relationship between delta S and delta A. So the surface delta S, the area of the delta S, the relationship between delta S and delta A is governed by this equation. So delta S is equal to delta A divided by cos gamma, where a magnitude of cos gamma. So if you look at our gamma here, if gamma is equal to 0, that indicates to us, that tell us that delta S and delta A are parallel. Okay, so if they are parallel, then gamma is 0, and we know cos 0 is 1. So from there we get delta S is exactly equal to delta A. But if gamma is not 0, then delta S and the relationship between delta S and delta A is equal to this. Okay, so delta S is equal to delta A divided by magnitude of cos gamma. And from the Riemann sum from double and triple integral, if delta S is very small and delta A is very small, and we do the summation, then delta S and delta A will be replaced by ds and dA respectively. So the relationship between ds and dA is ds is equal to dA divided by cos gamma, magnitude of cos gamma. Okay, now let's look at how to get ds in terms of dA. So let's say the surface sigma is written as z equals fxy, but if we rewrite the equation, we can write the surface as a function of x, y, and z. So let's call that phi. Phi of x, y, z is equal to z minus f of x, y. Or you can write it as fxy minus z. It doesn't matter either way. Then from the previous chapter, the normal vector to the level surface is equal to the gradient of phi. This is from the previous chapter. So the gradient of phi, or del phi, is equal to the normal vector to the level surface, which is equal to differentiate phi with respect to x. That will give you minus partial f partial x. And the y component, differentiate phi with respect to y, you get minus partial f partial y. And then the z component is when you differentiate phi with respect to z, so that will give you a 1. So that is the normal vector. Now, we know when you dot two vectors, dot product of two vectors, n dot k. So here, this is our n. Okay, and our k, if we write it using the pointy bracket, that would be 0i plus 0j plus 1k. So from the definition of the dot product, n dot k is equal to magnitude of n times magnitude of k times cos gamma. And if you take the magnitude of that, then cos gamma, you have to take the magnitude of cos gamma as well. But we know the magnitude of k, which is a unit vector, is equal to 1. So rewriting that, we get cos gamma, magnitude of cos gamma, is equal to magnitude of n dot k divided by magnitude of n times magnitude of k. But we know magnitude of k is 1. So in the denominator now, we only have magnitude of n, which is magnitude of normal vector. And when you dot n and k, so this is our n, that's the normal vector to delta s or ds. And this is our k. So when you dot the two vectors, what you get is, okay, let's see here, n dot k. It's going to be a scalar. So x component multiplied with the x component, so that is 0. Y component multiplied with the y component, that is 0. Z component multiplied with the z component, that is 1. So n dot k is equal to 1. Okay, so simplify this. Cos gamma, magnitude of cos gamma is equal to 1 over magnitude of n. Then rewriting this, remember ds is equal to dA over cos gamma. So from there we get ds is equal to dA divided by cos gamma, and cos gamma is 1 over n. So rewriting that, we get ds is equal to magnitude of the normal vector times dA. So that is ds. When we project our surface sigma onto the region on a plane, then ds is equal to magnitude of normal vector times dA. Okay, so fxy z dx, integral over surface sigma, can be evaluated by projecting surface sigma onto a region. Then ds here is equal to magnitude of normal vector dA. Okay, now I'm going to show you how to evaluate this. Okay, all right, so here we have a theorem. How to evaluate this, or where to project our surface sigma onto, on which plane do we want to project surface sigma onto, depend on how the surface sigma is given. So here we have a theorem. We have A, B, and C. Okay, so we have 3 items. Wait, we have 4 items. Okay, now let's look at the first item. So if your surface sigma is given as z equals a function of x and y, so what you need to do is you need to project your surface sigma onto the xy plane. So project your surface sigma onto the xy plane, and then replace z here, whatever your function fxyz. So z here must be replaced by g of xy, and ds is really the magnitude of normal vector dA. So this would be the magnitude of the normal vector. Okay, so it's equal to partial g partial x squared plus partial g partial y squared plus 1, and then integrate over region R, which is on the xy plane. Now let's look at the second case. If sigma is given as y as a function of x and z, you need to project your surface sigma onto the xz plane. Okay, need to project your surface sigma onto the xz plane. And when you see y here in your function, so y must be replaced by g of xz. So everything now would be in terms of x and z. We don't have y anymore. And ds here would be the ds here would be the magnitude of the normal vector dA. So that would be partial g partial x squared plus partial g partial z squared plus 1, and then integrate over region R, which is on the xz plane. Now let's look at the third case. The third case is where your surface sigma is given as x as a function of y and z. So if you have this case, then you need to project your surface sigma onto the yz plane. Okay, project your surface sigma onto the yz plane, and z here in your function f is replaced by, you should replace it with g of yz. So now everything are in terms of in terms of y and z. You don't have x anymore. And ds here would be equal to the magnitude of the normal vector dA. So that is equal to square root of partial g partial y squared plus partial g partial z squared plus 1. And then integrate over region R, which is on the yz plane. The last case here is where your function here is equal to 1. So if you only have ds integrate over surface sigma, when you integrate this, what you calculating is really the surface area of the surface sigma. So if f is equal to 1, you only integrate ds. So ds here is just, so that would be magnitude of normal vector dA and your region R. So your region R is your region where you project the surface sigma onto. So it can be on the xy plane, yz plane, or xz plane. So, but the bottom line is, if you integrate ds of a surface sigma, what you're calculating is the surface area of your surface sigma. Okay, so that is line integral over a scalar field. So what you need to do is you need to project your surface sigma onto a region, and ds here is magnitude of normal vector dA. Okay, for example, I'm going to save that in our next video. Thank you.